Welcome all. Today we can discuss the design of springs, some problems related to design of springs, some previous question paper problems. This is a question. A rail wagon of mass 20 tons is moving with a velocity of 2 meter per second. It is brought to rest by two buffers with springs of 300 diameter. The maximum deflection of the spring, is 250 mm. The allowable shear stress in the spring material is 600 megapascal. Design the spring for the buffers. Okay, here the mass of the rail wagon is given as 20 tons. That means 20 into 10 raised to 3 kg. That rail wagon moving with a velocity of 2 meter per second. It is brought to rest by two buffers with the springs of 300 mm diameter. The spring coil diameter is equal to 300 mm. The maximum deflection of the spring delta is given as 250 mm, and the allowable shear stress in the spring material is 600 megapascal. Okay, then coming into the solution, given m is equal to 20 ton, that's equal to 20 into 10 raised to 3 kg, and v is equal to 2 meter per second, and capital D is equal to 300 mm given, delta is equal to 250 mm given, that is maximum deflection. Then allowable shear stress is equal to tau, that's equal to 600 megapascal, that's equal to 600 Newton per mm square. Then first the calculation of the diameter of the spring wire, small letter d. Small letter d is equal to diameter of the spring wire. Then first we have to calculate the kinetic energy of the wagon. First we have to calculate the kinetic energy of the wagon. That's equal to half mv square. Here the mass of the rail wagon is given, and v, small letter v, velocity of the wagon is also given. Then that's equal to 40,000 Newton meter, or 40 into 10 raised to 6 Newton mm. Next, let capital W be the equivalent load which, when applied gradually on each spring, causes a deflection of 250 mm, where W is the equivalent load that will cause a 250 mm deflection when it is applied gradually on each spring. Then that W into half into delta into 2, that's equal to energy stored in the springs. Energy stored means that half into W into delta. This is the energy stored in the spring during the deflection when we applying the equivalent load, capital W. That energy is equal to half into W into delta. Then that multiplied by 2 will give the energy stored. Since there are two springs, then energy stored in both springs is equal to half into W into delta into 2. Then that is equal to 250 W Newton mm. Then we can equate this energy stored in the spring to the kinetic energy of the wagon. Then we can calculate capital W, equivalent load. Here, equating equation number 1 and equation number 2, that W is equal to 40 into 10 raised to 6 divided by 250. 40 into 10 raised to 6 divided by 250, that's equal to 160 into 10 raised to 3 Newton. Then we know that the torque transmitted, already we discussed this equation torque is equal to W into D by 2 during the theory portion, discussion of the theory portion of the designing of springs. Then that T is equal to that torque is equal to W into D by 2, W into capital D by 2. Capital D is the diameter of the spring coil. Then that is equal to 160 into 10 raised to 3 into 300. Capital D is equal to 300 mm. 300 mm. That 300 divided by 2. That's equal to 24 into 10 raised to 6 Newton mm. Here 300 is in mm. So this torque must be having a unit of Newton mm. Okay. Then this is the torque transmitted by the spring. Torque transmitted by the spring. And we know that this torque must be equal to pi by 16 into tau into d cube. When we discussing the theories of failure, we got this particular equation while considering the theories of failure related to shear stress. The torque, external torque, must be equal to pi by 16 into tau into d cube. Then we can calculate a small letter d, diameter of the wire, by equating these two, and we will get that d as small letter d as 58.8 mm. Then we can say that d is equal to 60 mm. 60 mm. This is the procedure to calculate the diameter of the spring wire. Next, number of turns of the spring coil. Let n is equal to number of active turns of the spring coil. Then delta deflection, delta is equal to 8 W d cube n divided by G d raised to 4. We can get this equation delta is equal to 8 W d cube n divided by G d cube from the KM data book, page number 170, equation number 11.6. Then we know that this delta is 250 mm here. Then we can apply all the corresponding values of W, D, G, and small letter d, etc. Then we can calculate this small letter n, number of active turns. That's equal to 250 is equal to 31.7 n, taking G as 84 megapascal. Then n is equal to 250 divided by 31.7, that's equal to 7.88. We can select that n as 8. Then assuming square and ground ends, we know that the total number of turns is equal to number of active turns plus 2. Then here the number of active turns is equal to 8. Then total number of turns is equal to 8 plus 2. 8 plus 2, that is equal to 10. These are all discussed during the theory portion of the designing of springs. Then free length of the spring. We know that this free length of the spring is equal to, here free length of the spring is equal to total number of turns into diameter. That's equal to total number of turns into diameter, that is the solid length of the spring, plus maximum deflection delta, plus this clearance 0.15 delta, that must be equal to the free length of the spring. Then we can calculate that is free length as 887.5 mm, 887.5 mm. This is the free length of the spring. Then finally, pitch of the coil. We know that pitch of the coil is equal to free length divided by n dash minus 1. Free length divided by n dash minus 1. This is the pitch of the coil. That's equal to 887.5 divided by 10 minus 1. That's equal to 98.6 mm. 98.6 mm. Okay. That's all about today's presentation. Thank you. Thank you all.